Hello, we are in lesson 5 corresponding to Gauss's law. In the introduction, we already saw the concept of flux, then we stated Gauss's law, and now we are going to apply it to solve a problem. We are going to calculate the electric field created by a surface charge distribution. But first, let's remember that Gauss's law tells us that the electric field flux through a closed surface is equal to the net charge enclosed inside it divided by the electric permittivity in the vacuum epsilon sub 0. The mathematical expression is as we see on the screen. The flux corresponds to the surface integral of the scalar product between the electric field and the differential vector of S. And Gauss's law tells us that it is equal to the enclosed charge divided by sub 0 epsilon. In the drawing, we have represented a Gaussian surface enclosing this point charge Q. At point P, we have chosen an area differential, and we have posed the two vectors with which we are going to work, the electric field vector and the differential vector of S, which remember is a vector perpendicular to the surface at that point and outward. Gauss's law allows us to calculate in a simpler way the modulus of the electric field created by charge distributions with symmetry. In this case, we are going to calculate the electric field created by a surface charge distribution of density sigma coulombs per square meter, an infinite plane. We are going to calculate the electric field at a point P located at a distance h from the distribution. The steps to follow are as follows. First, we must ask ourselves, how is the structure of the electric field we are looking for? That is, how are the field lines? Then we will choose a suitable Gaussian surface. It has to be an equipotential surface. Then we will calculate the electric field flux through this chosen surface and see what charge it encloses. Finally, we will apply Gauss's law to clear the modulus of the electric field we are looking for. Well, first of all, what does the electric field structure we are looking for look like? We have the infinite plane charge with sigma coulombs per square meter. If we choose the point P where we are going to calculate the field, which is at a distance h from the plane, we can make this vertical coincide with the z-axis. So this would be the x-axis and this would be the y-axis. In this quadrant, we could choose a differential surface element that would have 3 symmetrical elements. If we graphically represent the electric field created by these 4 area differentials at this point P, we can observe graphically that the horizontal components cancel out and only the vertical component remains. The same would occur at any point in space, since the charged plane is infinite. The modulus of the electric field in this case could depend on the distance h from the plane. Well, next we are going to choose a suitable Gauss surface. It has to be an equipotential surface. Recall that equipotential surfaces are those to which the electric field is perpendicular at all points. In this case, as the electric field is vertical, the equipotential surfaces are going to be horizontal planes parallel to the charged plane. The Gauss surface has to be a closed surface, so this equipotential plane is not enough. What we are going to do is to choose a cylindrical surface. And we are going to close it with caps 1 and 2, which are going to be equipotential surfaces. Then, therefore, the closed Gaussian surface is going to be a cylinder of height 2h and base with area A. Next, we are going to calculate the electric field flux through this Gauss surface, and we are going to see what charge it encloses. The total flux will be equal to the flux through surface 1 plus the flux through surface 2 plus the flux through surface 3. On surface 3, the flux is 0, since at any of its points, the electric field vector and the differential vector of that are perpendicular. Therefore, the scalar product of these two vectors is 0. On surface 1, the electric field vector and the differential vector of that are parallel. Therefore, the scalar product between these two vectors is equal to the product of the moduli. In addition, all points on surface 1 are at the same distance h from the charged plane. Therefore, the modulus of the electric field will be constant. Under these circumstances, the flux is equal to the electric field modulus times the area A. On surface 2, the same thing happens. The electric field and the differential of that are still parallel. Therefore, the scalar product is equal to the product of the moduli, and the electric field modulus is also constant. Therefore, it leaves out the integral, and we are left with the flux equal to the electric field modulus times area A, exactly the same as in surface 1. Then, the total flux will be equal to twice the electric field modulus times A. The charge enclosing this cylinder is equal to the striped area A multiplied by the sigma coulombs per square meter. Finally, let's apply Gauss's law, which tells us that the flux we just calculated, and which is equal to twice E times A, is equal to the enclosed charge starting from E sub 0. Since the enclosed charge is sigma times A, we can clear that the modulus of the electric field is sigma split 2 epsilon sub 0. Note that it is independent of the height hh of the cylinder we have chosen as Gaussian surface. To give the vectorial character to the electric field, we distinguish between the zone above the plane and the zone below. For positive zeta, the electric field is positive, and we have to multiply the modulus by the unit vector k. While in the lower part of the plane, for negative zeta, the electric field will be negative, and it is necessary to multiply the modulus by the vector minus k. Finally, I wanted to plot the dependence of the electric field modulus created by a surface charge distribution of sigma coulomb square meter as a function of the distance to the plane. As you can see, it does not depend on the distance to the plane at whatever distance we are, and it is always constant, being positive for positive zeta and negative for negative zeta. And that's all. Thank you very much for your attention, and see you next time.